In today's video, we're going to talk about how to count significant figures. In today's video, we're going to learn why significant figures are important. We're going to learn the basic rules for counting significant figures, and we'll do lots of examples. So, in order to give you an idea what significant figures are, I want you to imagine that you ask 3 friends to find the mass of a baseball. And you have these 3 friends and they come back with different answers. Your first friend says the mass of the baseball is 200 grams. The next friend 148 grams, and your last friend 148.000 grams. Alright. Significant figures are those digits in a measurement which add to the precision of the measurement. So of these 3 friends, which measurement is most precise? Well, for reasons that we'll talk about later, the one on the right is most precise, 148.000 grams. We can imply that the friend on the right must have used a very precise or very sophisticated instrument. Maybe she has an analytical balance at her house or something, and she was able to tell you the mass of the baseball very precisely. Meanwhile, the friend on the left, because he said 200 grams, we can assume maybe he was just taking a guess, right? Now I want you to think about what difference, if any, there is between the 148 grams and 148.000 grams. Is there any difference between those two measurements? So let's talk about rules for counting significant figures. First rule is that all non-zero digits are significant. So as an example, this figure 3.89 grams has 1, 2, 3 digits. They're all non-zeros. So we'll say 3 significant digits. 489,541 meters. We have 1, 2, 3, 4, 5, 6 significant digits. They're all non-zeros. We don't even need to consider it. There's no question about it. Next, 0.891 seconds. All of those 3 to the right of the decimal points are non-zeros. So we'll count those as being 3 significant digits, no question about it. So the rest of the rules that we're talking about mainly apply to situations where you have zeros. So rule number 2 states that zeros between 2 significant digits are themselves significant. So if we look at this example here, we learn from rule 1 that the 4 and the 9 are significant, and rule 2 states that anything then between significant digits is also significant. So that makes this digit here significant. That 0 there is significant. So we have 3 significant digits in that figure, 409 kilograms. Same thing applies here. If the 6 is significant and the 4 is significant, then that 0 must also be significant. So for this next example, we know that the 1 is significant. We know that the 2 is significant. Neither one of those 2 digits is a 0. So then everything else between comes into play as a significant digit. And so we would say that we have 5. Rule number 3 states that precision zeros are significant. So what is a precision zero? A precision zero adds to the precision of the measurement and can be found to the right of a significant figure and to the right of a decimal place. So to the right of a significant figure and to the right of the decimal. So let's look at an example here, and we have 36.0 grams. 36.0 is different than 36. We have 3 significant digits here because this 0 here counts. Next, 36.00 grams. Notice this measurement's even more precise than the one before it. So here we have 4 significant digits in that we have 2 significant digits to the right of the decimal place, 2 significant precision zeros. Lastly, 19.8950 meters. Every time we add a 0 out here to the right of this decimal place and to the right of a sig fig, it counts. So if we count that up, that's going to be 6 significant figures. And now we can think back to our friends who took the mass of this baseball to be 148 and 148.000 grams. and we can see that her measurement had 6 significant figures, while this friend with the brown hair, her measurement only had 3. Next, we'll say that placeholder zeros are not significant. Placeholder zeros are zeros which do not enhance the precision of the measurement and only speak to the magnitude of the answer. As an example, let's look at this next measurement, 40,000 kilograms. These zeros here, they are to the right of a sig fig, but they're not to the right of a decimal. So they do not add to the precision of the measurement. So this one here has only 1 significant figure. Next, 0.006 seconds. These zeros here serve only to specify the size of the measurement. They don't add to its precision. So there's only 1 significant decimal place here. This 100 meters here, only this 1 is significant. Those zeros are not. So you end up with 1 significant figure. Our 5th rule has to do with scientific notation. And we have to remember that when we have numbers that are written in scientific notation, we only need to look at what we call the coefficient, not the exponent. So here I have 4.50. That comprises the coefficient. The 3 is the exponent. So when we're trying to decide how many significant figures are in this number, we only look at the 4.50. We do not look at the times 10 to the third. The times 10 to the third, that's where our placeholder zeros are, if you think about it. So this guy here is going to have 3 significant figures. Lastly, this is our last rule. Exact numbers or defined relationships are considered to be infinitely precise. So if we look at this picture here of these kids, when you say how many children are in the picture, there's exactly 4 children because we can count them. There's no ambiguity, there's no uncertainty. Similarly, if we're talking about this dozen eggs here, and you say, what is a dozen? A dozen is exactly 12 items. That is the definition of a dozen. So there's no ambiguity, there's no imprecision. That 12 is considered to be infinitely precise. All right. Now, sometimes it's unclear whether a number was counted or not. So we're not sure whether to employ rule number 6. And so if we get our first friend back again, he says that he has 1,000 baseball cards. If he actually counted those 1,000 baseball cards, then that number should be infinitely precise. But if he didn't, if that 1,000 is just a guess, then that is only 1 sig fig. So how can we be sure how to convey exactly what we mean? Well, this is where scientific notation is going to come into play. We can write this number here as 1.000 times 10 to the third and convey 4 significant figures. Or we can write it as 1.00 times 10 to the third if we mean to say 3 significant figures. We can write it like this if we want there to be 2 significant figures, or if we really mean that this is just a guess, we can say only 1 significant figure. So the beauty here is that we get to determine how our number is interpreted. When we report this 1,000 in our science paper or something, we get to be the ones to tell our readers how to interpret that 1,000, whether it is counted, whether it's somewhat precise, how much precision goes into that number. Alright, let's try some examples. Our first example here is 45,000.6. This, if you remember, goes back to rule number 2. This 4 is significant, the 6 is significant, therefore everything in between is significant. And we have 1, 2, 3, 4, 5, 6 significant figures. Next example, 630.0. We have to remember that this is a precision 0. It's to the right of a decimal place, and it's to the right of these significant figures over here. So we have 1, 2, 3, 4. 4 significant figures. Here, this one's a little more complicated. 890.0. Keep in mind that, of course, that first 0 serves no purpose except to, I guess, cosmetics, I guess, if you want to keep it there. It certainly doesn't add to the precision of the value. So we're not going to count this guy. But this 0 is a precision 0. And that 8 is significant, so then everything in between becomes significant. So this here should have 4 significant figures. How about this? 05.05 times 10 to the minus 7. Here we have again our coefficient and our exponent. So we have to remember to only look at this portion of the number. We discount the exponent. Of course, it's still there, we just don't consider it for sig fig purposes. And so we, again, the 0's placeholder, and we say that there are 3 significant figures in this measurement. This times 10 to the minus 7, remember those are our placeholder zeros. How about this is just a statement. Snow White lives with 7 dwarfs. This would be infinitely precise. These dwarves are counted. We know exactly how many dwarves there are because we saw the movie. And so that would be infinitely precise. Example number 6, here we go back to scientific notation. We're not going to worry about the exponent, it doesn't really play into things here. But now we have to start decoding what to do with this here. 60.0580. Of course the 6 is significant. This 0 here is to the right of the decimal and to the right of that 6, so it's significant. And everything in between becomes significant then by rule number 2. So we have 1, 2, 3, 4, 5, 6 significant digits. And I think this is our last example. Here's another statement. There are 12 inches in 1 foot. So again, here we have the idea that 1 foot is defined as 12 inches. So this here, this relationship is infinitely precise. That's the very definition of a foot. So in conclusion, today we've reviewed the basic rules for counting significant figures, and next time we're going to build upon this idea. We're going to discuss, now that you can look at a figure and count how many significant figures there are, now what do you do? How does this impact your rounding and your problem solving and data crunching? Thanks for watching, and I hope you have a great day.